Good morning to everybody. So, yesterday we discussed about the theory of ionizing electrodes and the basic constructions and measurement techniques or the special attention required for measurement of pH of a solution. So, we have seen that the measurement or the theory is based on Nernst equation. That is, two half cells are to be connected, and two half cells, each one will have its potential developed, and that is given by the Nernst equation. So, in this way, using a measuring electrode and a reference electrode, we could measure the voltage and we could relate it with the pH value there. So, in this way, actually, not only hydrogen but many other uh, ions can be detected. And in fact, without going to the detail, uh, another type of similar is there, sensing technique is there, which is called oxygen gas analyzer. So that means it can also be, the similar technique can be also used for oxygen gas analysis. Oxygen gas analysis means basically what is the percentage of oxygen present in your in the gas which you want to detect. And that is particularly used for combustion control. This combustion control is nothing but in a boiler, what is there? We primarily generate heat by burning coal or fuel or I mean, yeah, there, mineral oil or something there. But so basically, it is burnt with carbon and oxygen are burnt to form carbon dioxide. But so if we do like this one, what we require for the particular amount of carbon, we require equivalent amount of, or rather compatible amount of oxygen, so that the burning is proper there. If the burning is not proper, there could be two cases. One is a incomplete combustion, then we will find that the coal or like this there will be several carbon particles will be in, will be coming out of the chimney. There will be several carbon particles coming out of the chimney, and which will create pollution. But the actual scenario what we like is that the oxygen is given exactly the same required to burn all the carbon particles there. And if the oxygen quantity is more, basically it will also carry a good amount of heat with it. So for a particular combustion control, we want to say that okay, it should be just oxygen should be supplied, should be just sufficient to uh, complete burning of the all the coal which are present there, or slightly less, more than that, so that we can ensure that if it is there is a small amount of oxygen there, we can ensure that the combustion is complete there. So what we see is that often these chimneys, which we have seen it must be in power plant or like this, these chimneys are there. So you will find if there are incomplete combustions, we will find the black fumes are coming like this there. And if it is a complete combustion, or say suppose more oxygen is going, there would be, we will find it, the carbon particles are not there, indicating area. So what is important is that from the, this is called a flue gas. In the flue gas, we want to find out what is the oxygen presence in this one. So that's why we call it oxygen gas analyzer. Another type is also there, that is dissolved oxygen analyzer. in a water or like this, where we need to find out the what is the for the pollution monitoring of the pond or like this, so that there is sufficient dissolved oxygen to cater the need of the fish or the or other species like this. That dissolved oxygen is a slightly different technique, but first of all, I will try to explain this oxygen gas analyzer, which I told that it is almost similar principle as in the case of pH gas, this one. So this probe is basically used in the case of PHA there, we used glass electrode. Here, this probe is basically zirconia type. And here it is basically zirconium oxide. So, this probe is a zirconium oxide there. So, it says that a pure zirconia tube, which is basically a tube made of zirconium oxide there, at high temperature, which is greater than 700 degrees Celsius, will develop potential between two surfaces that is a function of oxygen ion concentration in contact with the surface. So it is similar, but here for the gas, everything is in the gaseous state. So first of all, the gas has to be heated above 700 degrees Celsius, and in that case, if some oxygen, sorry, oxygen ion comes into contact with the zirconia tube, then across the two surfaces, that means outer and inner surfaces of the zirconia tube, there would be a potential developed, and this potential will be a function of the oxygen ion concentration. Let us try to see how does it look like. what we have, that this is a zirconia tube. This is a zirconia tube. We will have to somehow heat the zirconia tube, and it becomes more than, the temperature becomes more than 700 degrees Celsius. The outer surface is exposed to the unknown measuring gas. That means it is dipped into the atmosphere, where we want to find out the concentration of the of the oxygen ion. And in the inner surface, we pass basically air, clean air with 20% oxygen. We know clean air has got 20% oxygen. We regularly pass through it. So this is the inner surface has got a oxygen concentration of 20%, and the outer surface we want to measure what is the unknown concentration. So naturally, what we can say, that these two, and in between there is a zirconia tube. These two electrodes form as a measuring electrode and a reference electrode. And we will see the potential developed. So basically we can say this is like these two half cells there. And the potential developed, the is basically E0 is equal to 0.0215 into T into log natural O2R divided by O2, and T is the temperature in Kelvin, which is greater than 700 degrees Celsius, and E2R is the reference, what we can say, sorry, O2R is the reference gas concentration of oxygen, that is 20%, and O2M is the unknown gas concentration of oxygen. So basically, if we look at it, this equation actually, though maybe the coefficients may be different or like this, it looks like as if two potentials we have developed. One is outer surface, one is on the inner surface, and we are measuring the difference of this potential. So basically, two half cells, this can be similar to your Nernst equations. You can say two Nernst equations, and two potentials developed across these two Nernst equations, and we can get it. And here you can easily see that the oxygen ion concentration and the potential developed, there is a functional relationship between them, and we can calibrate it with this one. So wherever you need to establish a combustion control unit or like this, or monitor the combustion, whether there is an unburned carbon particle or not, whether the combustion is proper, because nowadays with stricter pollution control mechanism. So these things, oxygen gas sensor is one of the very useful instrument detected by this one. As I told, there are many other things there which I will not discuss. Uh, Basically, the dissolved oxygen ion, the blood sugar measurement, and those things. So if I think maybe in the next course, that is a advanced sensing technique in the final year, some of the topics may be discussed. But there are nowadays a lot of measurement principles, newer measurement principles are now available there. I would be discussing another type of related measuring technique, which is really rather completely different from this E there. Of course, they are all based on the Nernst equation, but outwardly uh, there is it is a different technique there. Let us go back to pH measurement here, because often this pH or similar type of not only the pH but also blood sugar or many other things we require to measure there. But the pH electrode, what we have is the glass electrode, which is bulky, which is not very handy, like this there. Whereas I want, and what we have also similar thing there, that's a, the sensor should be very small in size and maybe use and throw type. You must have seen for blood sugar measurement now the kits are, those things are available. So those things are basically use and throw type there. And similar techniques are also available there for the hydrogen ion concentrations also there. So basically, they are actually called ice fit. In short, it is a short form of ion selective field effect transistor. So it is a general name, so it could be hydrogen ion or it could be some other ions also, maybe there. Uh, so these things can be used for the, and naturally it's basically, if you look at it, it's constructionally it is very close to the rather it is primarily a field effect transistor. So this field effect transistor gives you direct electrical output and we can do the things there. So in short, what we call it so this ice weight is not only for hydrogen, actually depending upon the reagent we use, depending upon the what is your requirement, we can have different chemicals or like this, and also different types of ion selective fate we can make it like this, but it's a general category of another type of sensors we have it. But it is advantage is that very small size, use and throw type, and also gives you direct electrical output which is measurable, not to be amplified there. So if we look at it, it's basically a MOSFET that incorporates sensitive sensor membrane directly on the gate area. So basically, earlier we know this basic MOSFET characteristics and etc. By applying the gate voltage, depending upon the gate voltage, the IDS, VDS characteristics we can change or like this. But in this case, what is happening? There is a gate area is reconstructed in a different manner. I mean, it is fabricated in a different manner, so that there is a scope for giving a view one drop of the liquid you want to measure, and here there very small amount of liquid you give it there, and from there it gives you some electric area there. So naturally, wherever the sample size is very small amount of sample we can do it, and it is basically use and throw type. You must have seen. So it could be blood urea also, all the things there. So different types of reagents we use it for different types of reagents. So I am showing you simply for pH only, but similar constructions we can have it. So what we can before do is what we can say is that advantages. One is very small dimension, which is 1 to 2 millimeter square area. You can see it. Second thing is that fast response and gives you direct output there. And third one is that no shielding is required. These things we will discuss afterwards, but we can say that earlier it was a sensor and a measuring circuit. You will have to connect it through wires there, and these wires requires particular shielding. Always it is better to have shield it from the so that it is basically in from outside world it is interference is less because often it may be get corrupted there. So these are the very fast response and very low. So naturally, it's also low cost type. Now, if we so look for the pH type one, what is its construction? Let us try to. Sorry, this is not drain. This is the base, and this is your drain. And we apply some voltage between drain and base there. So this is the substrate, and here we have this is the gate area where there is an insulator, and over there what we do is that make some sort of cup where one or two drops of liquid we can pour on it. And over here we put an electrode there and to make it the gate here. So what we have, it's a gate insulator which is basically silicon nitride for oxygen I am telling, or aluminum oxide here. We put some insulator there. And here we few drops of test liquid is poured here. And we have a what we call it a reference electrode. Okay. Then, without going into the detail of it, we can say that okay, I put some extra voltage here and vary VGS, and this is your A there, characteristics there. So, what is happening is that what it says that you put 1 or 2 drops of this one, and this is a ion selective insulator like this, the silicon nitride or aluminum hydroxide, where the depending upon the pH concentration of the liquid here, that will change the gate current of it there or the overall uh, characteristics of the MOSFET. If we look at it, that VDS IDS characteristics changes like this there. Low value of pH and high value of pH. So basically, if the pH is high or low, that changes the characteristics of the MOSFET, that is the VDS IDS characteristics, obviously for a particular VGS. If we change it, the characteristics will also change. So you can easily see that this MOSFET is a very convenient one because it's a very small size. You can put 1 or 2 droplets of this one and it will change this one. And in an integrated circuit, you can have the output voltage also from this one and give some output, analog output voltage there. So it's a very small size, as you have seen that it is 1 or 2 millimeters of the area. And also, if you want to test any liquid, very small amount of liquid will do. And normally, they are use and throw type, but its cost is low. You can be afford that one there. So this is another type of course, what I wanted to say, there is another group of that is what is called ice fate. Sometimes they call it chem fate, or this is another group of fates are there which can be used as sensor for detection of the few definite ions there and concentration of the few definite. I have shown it for A there, hydrogen ion concentration only, but which ion concentrations or some other types of different types of ions concentration or the liquid A there, we can nicely measure that one. Is it okay? Any question? Any question? So, if it is not, I will be, because I know that I can continue for far more but this one, but the time is short, I will have to be very brief. But you can do it. These are not very difficult. A lot of sensors, newer sensors are coming, newer sensing materials are coming, and these things are there. But definitely the problems are also coming that problems are also, so basically what we want is that newer materials are coming, so newer sensing techniques are there and we can have a better and ear sensing here. But also if we look at it, this is your sensor and this is your signal conditioning or measuring circuit. So these two we normally connect through wires. Normally earlier we used to connect, and normally still that one. The sensor is one identity. We have another measuring circuit or a PCB or a EA there. It is connected there and connected through EA there. Through wires, a bunch of wires are like this. Mostly they are analog in nature, but there are few sensors. We provide you digital one, but it is very small there. So the major problem is that you have the sensor output voltage is very small, because if we want to have very sensitive one, the sensor output voltage may be in terms of microvolt or like this there. So naturally, the thing we require some amplification of the voltage, and the readout, and a signal conditioning circuit should also be capable of amplifying to a high one there. But there is a problem there. The problem is that there could be some interference. What do you mean by interference? Some external signal, unwanted signal, or these things are often coming here and disturbing that one. And that signal may be very high magnitude compared to this sensor signal, which is a very small one there. So, naturally, as the voltage becomes smaller, the sensor voltage becomes smaller and smaller there, and you need to have a higher gain measuring circuit, very powerful measuring circuit or like this there. We need to also ensure that the it amplifies only the signal, but this noise and etc., what we call it noise, which are unwanted signal or like this, they are not amplified or they are rejected continuously. And if we one also one common sense is that if we bring sensor and the measuring circuit closer, these wires are we make this very as small here there, we can say that okay, that will be, there is less scope for the interference of the external signal. So naturally, closer the gap distance between the sensor and the measuring circuit or signal or whatever may read out or like this, it is always better, because there is a less scope there. And now what we have on this is one of the cases, what we call it an IC sensor, basically, where the sensor and the measuring circuit are all integrated. They are integrated on the same structure, because here itself on the same base you can we can have the further signal conditioning and amplifiers are like. The advantage of this one is that this one, that is the wires connecting the sensor and the measuring unit, is where which is very prone to this interference and all these things there. That can be avoided. So that's why people try to go for as integrated sensor as possible, because the major issue and major, as we are going newer and advanced type of sensors or sensing techniques there, the major issue is always that okay, whatever you are getting is reliable, the reading is reliable, is sensitive to the particular input which we are interested about, others are not. So naturally, what we call it is that the signal to noise ratio also sometimes they are ADA. These things you can have, that what type of, basically, what we can say is that uh, deviations and unwanted signals which can create and vitiate the actual output there. It could be, one is what we call it electronic noise. What is electronic noise? Possibly you have studied this one, or maybe it will be studied there afterwards, or like this. You know, any electronic device do have this generate some noise always there. They call it, sometimes we call, some of them are thermal noise. If we have a resistor, it will always be generating some noise voltage or like this there, due to the random fluctuation of electrons there the inside, and it depends upon the temperature or like this. So this we could say one is a thermal noise, one is flicker noise, one is 1 by F noise. One is 1 by F noise, and etc. there. So there are a lot of there are a lot of noises are there, which will be basically generated in the electronic circuits there. That is a there. That is the amplifier, diodes, resistors, and etc. So this is an important thing, and mostly they are characterized by their, what we call it is the uh, their they are random in nature. They are characterized by some statistical by the standard deviation, frequency spectrum, and all this sort of things there. So this is one thing we need to look into it. Okay, we'll have to do it. We are amplifying it. But the point is that there would be always some random noise would be generated because of in the resistor, in the amplifier, in the fade, or other types. And also it depends upon whether it is you are using in low frequency region or high frequency region, and these are the things there. So this always, it's important to estimate. We have made a circuit to estimate what is the noise and how the noise will be able to interfere or this one, and it will affect the measuring circuit. And we will always try to see that always that there is some limit beyond which, if the signal is low, if below, if it is below that threshold or like this will be masked by the this signal will be masked by this noise there, and will not be able to detect the signal in presence of noise. So often we come across the term that is a SNR, that is a signal to noise ratio. That means how good is it? It should amplify the signal and it should reject the noise or any frequency, other frequency or random noise there. It is very important that it is how good it is there. So we'll have to, while designing, as I told, that it is an instrumentation device is not only knowing the what sensor you are using, what is the principle, but also the construction, how do you place it, and actual situation. What is the signal conditioning circuit? And also important, how do you connect this thing through wires? How do you connect through these wires the sensing scheme circuit and sensor as with the measuring circuit? All these things will be affected. So even though you have a good sensor, but because of the improper grounding, improper connections or improper grounding itself. Okay, I told I have not come to that level of grounding. Those things will come to that one afterwards. But that may vitiate the corrupt the signal and will not be able to read anything meaningful of it. Or even though if it gives you, it will be a wrong data or wrong signal it will give it. So naturally, we must be very careful about these things also. That is, one part is that how much is the electronic noise, how does it affect, and etc. And second thing is that what are the interference, because there could be other signals or going by nearby, and naturally what we'll have that their signals are there, they may also interfere like this. So in a nutshell, we have to look into also the we have to look also into that is a noise and interference. Whatever may be good circuit, good scheme there, but if the it is not properly coordinated, the measuring circuit is suitable for the sensor, if it is uh, the wires are not properly shielded, yeah, those things will cause you the deterioration of the signal there. So this is very important for us to study those things there. So that part we'll discuss. For an example, we can say that okay, uh, uh, the loading effect. Loading effect is a very important one. If we have a signal, if we have a source, we have already showed that there is a source there, and any signal I can modulate. There is a source here, uh, Vs, there is a Ri, and there is some measuring scheme like this there. And to avoid loading effect, we know that Rm must be much higher than Ri there. But sometimes it may happen, particularly the pH electrode we have already seen. Its Ri is in gigaohm range or like this, and which we have already discussed in this one. So if we are not selecting the RM, that is the measuring circuit properly, we may not be able to get any signal out of it, or whatever may be. The sensor may be good, but this signal conditioning circuit is not appropriate for that one, and that may cause the deterioration of the voltage online. So we must look into the also the proper choice of the sensor and the compatibility of the sensor and the measuring circuit, and also look into the different noise analysis, what we can say, and look into the interference of this one there. So I will take a break after that, and then we'll discuss about what we call it a noise and interference.